Good evening. Welcome to another video lecture. In this lecture, I'm going to talk about electric potential. But in order to do that, first I want to review some other concepts that we have covered throughout this year on energy in general. So to start off here, I have a ball, a racquetball. It's pretty elastic, bounces right back up. Now, this ball has some energy due to its position, and we refer to that as gravitational potential energy. So it's potential energy here. When I let go of it, that energy is converted into kinetic energy. As it falls down, it gains speed. That the potential energy decreases, the kinetic energy increases. Potential energy is just energy due to position. Now, if we remember like a spring, so we have spring potential energy, which is how much a spring or something like that is stretched. So it's due to the position of the spring. So I can stretch the spring out, and it has more energy. So I'll put that here. Spring. All right, back to the ball, for example. Now, if I want to change the energy of the ball, I need to do work. So if I want to change the potential energy of this racquetball right here, I need to do work. And by doing work, I'm applying a force over some displacement. So if I'm changing the energy, doing some work, I'm going to pick up this ball from A to B. So if I pick it up in the air, I'm going to change the energy. Within our realm, I'm increasing the energy right here, the potential energy. And this is really just the potential energy due to its position relative to the Earth. And so, I mean, it's position, one mass relative to another mass. And we say that work is equal to force times displacement. Now, this works for some situations. This idea of work being force times displacement works for small situations, and it doesn't really work with large distances with gravitational potential energy. And as we'll see, it doesn't really work with large distances of electric potential, as we'll start talking about that in a minute. But the idea here that work is a change in energy. You're doing work to change energy. Now, if you think of, I have some charge, and we're going to call this some positive charge at point A. This is this charge here. It has some value. Let's just give it a value of Q. What I'm concerned with, and what I am going to be looking at right now, is how much energy does it take to take another charge, and let's pretend this racquetball is that other charge. Take this racquetball and bring it in from, say, infinitely far away, and bring it in and put it right here, below A. How much work do I need to do in order to have that done? And what I'm doing there is I'm changing the electric potential energy. I'm going through and I'm going to be changing this electric potential energy of this ball. It's because I'm changing its position relative to another charge. So if this has some charge, whether it be positive or negative, doesn't matter right now, there's going to be some change in energy due to its position relative to this charge. The reason that this idea of work equaling force times distance or force times displacement doesn't work out, what we won't be able to look at it within our class. You need to be able to use calculus and do integrals to be able to understand the full properties that the changing force has. And that's what I'm kind of getting ahead of myself, is that the electric field or the force applied by this charge out here changes as it goes on, as you come close. So as I come closer to it, the force gets stronger. So if I move 1 meter like this here, I'm doing much more work because the force is much greater than if I'm moving out here. So that it's because both things, the displacement and the force, are changing at the same time, is one thing that we won't look at within this class. But what I'm concerned with is the electric potential energy of, say, this ball right here, and what we'll get to in a second, is electric potential. Now I'm going to write up some definitions and I'll come back in a second. All right, electric potential energy. It's the energy due to the position of a charged object. So at point, if we look at charge A right here, positive charge A, at point B over here, there's going to be some energy due to the position right there of this, due to your position relative to this charge. That's the electric potential energy. So it's measured in joules. It's a position relative to one other charge. Now the other idea that we're going to look at is electric potential, and this gets us on and moves us a little bit closer to where we're going to get into circuits with current and voltage. Electric potential is the energy at one point per charge. So if I have some point charge, Q, here, it's the energy per charge. Electric potential is written as a V. It's joules per coulomb is the unit for that. And its electric potential is equal to the potential energy at that point divided by the charge. So it's electric potential energy per charge. That's really what the electric potential is. When we look at and talk about voltage, we're going to talk about the idea that voltage is a difference in electric potential energy between two places, which really means that it's a difference in potential energy between two places based on how much charge there is. So we'll come back to that in a little bit later, but just understand this idea right now that electric potential, V, depends on the electric potential energy at that point and the charge. Thank you very much. Have a good night. I'll see you tomorrow in class. I should probably say, write down any questions and bring them in tomorrow, and we'll talk about them then. Thank you very much.